So for today's class, we are going to talk about energy-based model, and then we go over the score-based models, and gradually make the connection to diffusion models. So just to do a recap, like every other session, so far we have seen, for example, autoregressive models, which I hope that because every class I go over this, by end of the semester, you all need to know how to define these ones, like that, how to describe them at least. So autoregressive models, anytime that you basically gradually one data point at a time predict, for prediction at a given data point, the only thing you need is the previous history, okay, the previous data points. Then we talked about variational autoencoder, which the idea was that if you want to find these basically likelihood of the data, we need to do some integration over all possible latent variables. There are different versions we have seen that exist depending on how we define this joint distribution, and we can break it down as likelihood of z given x times the prior, or vice versa. In order to solve this, we saw that this is kind of intractable and it's hard to maximize this log likelihood if you apply log. Instead, we proved that this right-hand side, when you apply log, becomes an elbow, like a evidence lower bound. And what we do, we focus on maximizing the lower bound. By doing so, you're automatically maximizing this. So the lower bound had two parameters, that right-hand side, a parameter for the encoder and a parameter for the decoder. The way that we maximize is that you move in. So if you are trying to maximize this becomes the lower bound. When you go kind of like upward, this is a direction on the encoder's parameters. Then you will find this bound, and then you can move along this bound to the right or to the left, for example, and that becomes the parameter of the generator. So you want to find the optimal this and optimal that, and then you move along this direction, kind of like that. Every time, basically, you first optimize with respect to theta, move upward, and then with respect to phi, which is the parameters of the generator. And we repeat this process until hopefully we get to the point that is as close as possible to this maximum. So that becomes some sort of like an approximation for finding this log likelihood. Then we talked about the normalizing flow, and we say that, well, the idea was that in variational autoencoders, in order to go from Z, or like a generated or sample, random sample, to a data point, they are basically, there's no deterministic mapping. That means could be any Z, and when you do, you cannot go back from X to the same Z because it's not deterministic. And because it was intractable, this calculating this integration. So we talked about normalizing flow, which the idea is that let's use this, instead of just having an encoder decoder, let's change the idea. We still want to do latent variables. That means we still want to map from Z to X, but instead of having encoder decoder, what we do, we want to have a way to map Z to X, and this should be any function that is basically invertible, and it's kind of like it has this bijection from X to Y, and it should be invertible. That means you should be able to go back from X to exact same Z. And what we also talked about is that when you go from one variable to another variable, the change in the variable based on the function, it's straightforward, but the change in the distribution is not the same. Because whatever was the distribution Z, under this transformation is not going to be the same for X. So you need to account for that transformation. And that transformation is with respect to the gradient of this transform function. Okay, so that's why we have this term. So the distribution for the X comes from the density for Z times the inverse of, there should be there's an inverse inside, the inverse of this term. And why we proved that also, the reason there's an inverse is because the likelihood and the volume, they have a inverse relationship. When the volume basically, when the like is more likely, the volume becomes less. What? What's the relationship between likelihood and the volume.
And it was higher gradient?
No, just tell me with respect to volume and likelihood.
Likelihood should be small.
Volume increases, likelihood decreases.
Yeah. Yeah, when the volume is large, that means you have a large space. When you sample, the likelihood is small.
Yes.
When the volume is small, then when you sample, it's kind of like a denser region, so the likelihood goes up. All right. Okay, so that was the normalizing flow. And then we talked about GAN basically, and we say that, okay, there are different types of models, like generative models, that instead of, so all the previous model, we were focusing on maximizing the likelihood. We said that, okay, maximizing likelihood, it doesn't mean actually it's not always a good objective function, because you could have a high likelihood, but really bad data generated. So the idea was that could we go towards some sort of like a likelihood-free models? And that becomes the idea of GAN. Why likelihood-free? Because GAN doesn't need to see what's the likelihood of a data. Instead, it wants to compare two data points. So instead of basically look at the likelihood, we basically compare a generated data point versus the original data point, and we use a discriminator as a way to, as like a neural network, as a way to estimate if it's a good data point that we generated is like a fake or real. And the idea will be that we want the generator to generate good results, and discriminator be able to distinguish that. And then GAN, we talk about it, that it's not actually that easy to train GANs. Lots of caveats, or like lots of challenges GAN has. And but what we talk about, two things that we could change the, and if you look at the GAN objective function, the loss function, it should be pretty straightforward for you. That there are always two terms in GANs. Like the left term is you're trying to maximize this term. And what is that term? Likelihood, log likelihood of the real data. That means D is the discriminator. Anytime you think of GAN, just think of two objectives. One objective is that if I pick a real data and I pass it to my discriminator, the likelihood over there should be high. And the likelihood is high, that means the probability is close to 1. The log becomes closer to 0. So this goes around to 0 if your goal is minimization. So that's the first part. The second part is if I sample from the generator, I generate an image and I pass it to the same discriminator, it should produce a low probability. That's what the second part is. 1 minus probability, like the probability of being real for fake data or generated data. So it has two parts, like similar to the idea of like a binary crossing tree, right? It's kind of for the real data versus fake data. And then we talked about that, well, there are some challenges here. So there are two modified versions, Wasserstein, basically distance. It's kind of like an Earth mover. The idea was that, well, what if how much effort and how much basically data I need to move in order to convert one distribution to the other one. So the Wasserstein distance basically says that we have X, sample from it, same thing. This goes over to the discriminator. So the discriminator job is that to see if it's real or fake. And then you sample here and you pass it to a discriminator here for the generated image. So that becomes the Wasserstein. Then we talk about there's another type called FGAN. And the idea of FGAN was that instead of we define the divergence like Kale divergence or Shannon divergence, what if we want to pick like different types of functions? And we say that the idea of FGAN is that you can do that, as long as you have a function and you can basically find it like some sort of like a conjugate of that function, like it should be a convex conjugate, and you can use that to estimate basically this value. So instead of here F, instead of having this term or that term, we have this conjugate function that we use it as our basically function. So that becomes the main difference between FGAN and Wasserstein. And all of this is technically the two sample test. And that's the idea of behind the GAN is, we basically saw that, well, two sample test is not that easy to write. So let's use a neural network to predict that two sample test. And the neural network is the discriminator. So the discriminator, the answer that it gives you is kind of like that, what we wanted to get from a two sample test. It tells you that which one of these two are real, which one of these two are fake. So now, all of this model are good. You know, it's kind of like a, they are like a special GAN one. It's kind of like a, they're pretty strong, but the likelihoods, we always have this issue. It's kind of like intractable. It's hard to find. For GAN, the training is unstable. It's hard to evaluate. We don't even know how to evaluate GAN. It's hard. And one of the main issues that GAN has is the mode collapse. It could basically keep repeating the same types of image or same image over and over again. Now, the idea was that could we find another class of models that could help us solving this problem? And then the idea is that, okay, yeah, there's another class called energy-based models that we can use that. So the idea here is that with energy-based models that they are pretty flexible model architecture. We're going to talk about those. You can basically kind of, if you think about GAN, or if you think about energy-based models, there are kind of limitations of architect, sorry, GAN or flow-based model. Like we saw that, remember if in the flow-based series of layers that you can only use. It's not like you can use everything. And so the model architect, the neural network architect is kind of limited. And the idea here is that if you use energy-based model, you don't need to worry about that basically constraints anymore. You can, it's pretty flexible. It's stable training. We are kind of using some likelihood-based model for training it. It can produce a highly, basically high quality data. And it's pretty close to the idea. What you're learning here is going to be the building blocks for the diffusion class. So that's another thing about it. Now, let's first talk about something. So if you think about the probability distribution, P of theta, the first thing is that, which exists in all these models that we have, right? We have this P of theta, it's kind of like a building block, is really important. We're trying to learn it. Now, P of theta is that probability that your model, for example, generates. Now, one thing we know is that that should be a positive value. It should be as a probability, right? Which that condition is a straightforward. You can have a model, neural network, and force it to produce something positive, right? And that positive could be any of the function below. So you just want a positive output, right? But the challenge with this, this concept of probability that you want your model to produce is that making it to sum to one is not that straightforward. The idea of like having your neural network to produce something that sums to one for all possibilities is not as straightforward. Think about one example of, you have this image and you're basically, these are pixels and you're trying to fill these pixels, right? So if you try to fill pixels, your goal is to generate an image. So one of these images that you're generating is going to be the correct image. The other ones are not the correct one. So your goal is that when you fill all these pixels, the correct image has the highest possible probability, right? But if you just increase the probability of the correct image without decreasing the probability of wrong images or wrong combinations, they never sum to one. You see the challenge? You keep filling these pixels. If you put all those solutions that you have, the probability of total should go to one, but that's not straightforward because they're separate images. So you need to have your model in an architect somehow that if an image or if a data generated becomes really correct, high likely, it should increase the probability of that and decrease the probability of the rest, right? And does that make sense? So yeah, let's look at this analogy of a cake, a pie. So let's say you have a cake, and if you take a slice from this cake, okay, there is an impact, right? So if you take a slice from the cake, so cake has a fixed volume, right? When you take a slice, that piece that you took, it should impact the rest of the cake, the rest of the slices that you could have. So the size of that pie could be your probability density that you get from your model, and the rest of the cake could be the rest of the possibilities data that you could get. So there will be this relationship between those. Now, one simple example of this you can think is softmax, right? Softmax that we use, we will see that softmax is technically an energy-based function, which it guarantees that if probability of one goes up, the probability of the rest will go down, right? So you want basically architect like that, but so that's the idea that we're going to go over. Now, the solution here is that you have, so we have this model, G theta. That's your generator, parameterized by theta over an image. By default, your model is not normalized. That means if you pass all possible data to this model, and you look at the result, the probability of total won't sum to 1. So the easiest thing comes to your mind is that, well, let's normalize those, correct? And what's the easiest way of normalizing it? Divided by, if it's discrete, summation of total. If it's continuous, integration across all, right? So that becomes the idea here. So we want to normalize our model by dividing it by z theta, where z theta is going to be, because this is like for continuous, is going to be this integration for the function across all possibilities, right? And this is the same as volume, right? So you have a function, divide the function over the basically volume of that function. Why this will sum to 1 now, and that the proof is below. So if you just divide this by this one, like this definition, basically you have this g theta d of x that comes out, these two cancel out, goes to 1. Okay, so it's guaranteed that it will sum to 1. So that's the idea of the parameterization of these probability distributions. So for any probability distribution, this for continuous one, this condition should met. And actually, you have seen this everywhere before. Gaussian distribution, gamma distribution, they all have this term in it. So if you think about, for this basically exponential, e to the power of this minus that, which we all know it as a Gaussian distribution, this term is that z. So in order to make the Gaussian normalized, we divide it by that term. So that's what you have seen. If you go, for example, for exponential, if this is your exponential, the volume becomes this. When you do that, this comes out. That's exponential distribution. Same thing if it's go for exponential families, this you can apply. For all of this distribution that you have seen, they need to be normalized. And this has been there all the time. So you see the energy base, so we have been using it technically. Now, and exponential family also, just as a reminder, covers normal, Poisson, beta, gamma. These are basically all exponential family. So one also, this is for continuous, but if you think about in discrete distribution also, we also do normalization. If you think about the, like for example, Bernoulli, you have like theta xi 1 minus theta xi, correct? This guarantees the normalization, or whenever you have something like a mixture, alpha some theta plus 1 minus alpha times another theta. Anytime you see something like that, that's also normalization. Because this relationship between alpha 1 minus alpha is guarantees that always to basically be normalized. So now let's connect that, go back to what do you call that, examples that we have seen before. Let's go to autoregressive. In autoregressive, we know that in order to find the joint distribution of x and y and or here x and y or x and z, we can write this way: joint times conditional, and we also this term basically, if you expand the same thing as integration across all possibilities, that always sum to 1. So this is a proof of like autoregressive model is always normalized by default. So it doesn't need normalization factor. It's always the integration goes to 1 across all possibilities. And that's what one of the things about autoregressive is that they guarantee to give you the probability density function. The challenge with them was, well, you need to know lots of conditionals, right? And also it's sequential, it's like make it slow, right? But if you have those conditionals, it guarantees that you will learn the actual probability density function. Then we have the next thing is like a mixture models, and mixture models. Oh, this perfect. This is like a mixture model. So if you have two models, one parameters by theta, one parameters by theta prime, you can mix those two and ensure that you have a valid distribution. The only thing you need is some mixing coefficient alpha, 1 times by alpha, 1 times by 1 minus alpha. And that will guarantee that this will be a valid distribution. It always basically goes to 1. Okay, so autoregressive mixture of models, basically, they have that. Now, those are like scenarios, like this G of theta, this normalization factors, it's easy to compute. But what if you have types of model? This is actually not easy to compute. It's like it's more challenging types of models. Now, the idea here basically becomes, this is where the energy-based model comes. Now, the idea will be that, well, we are going to change our function. We're going to introduce some new form. So if you have this function f theta x, in energy-based model, what the first thing you need to do is bring an exponential behind the function, then divide this by this z of theta, which is the same normalization factor, but the z of theta becomes this with respect to the exponential of the function, not the function itself, right? So in what you saw in the first slide, there was no exponential. In the energy-based, you will add exponential over the function, and even in z, you will have that exponential. So here, this is the unnormalized model that you have, neural network. This becomes kind of like a normalized by exponential, and this becomes object normalized overall. This basically guarantees to that this will sum to 1. Now, what you also will see in theory, so this energy-based function comes from kind of like a thermodynamic ideas. So instead of f of theta, it's possible that you see exponential minus e theta of x. Okay, it's possible instead of f of theta, you see negative e of theta. The reason for that is e of theta is called energy function, and f of theta is your original function, but there's an energy version of it. And the idea is that when you have a region if you think about it as like a distribution, where you have a region that the density is high, the energy will be low. When the density, so think about it, let's look at it in 2D. So you have this contour, right? When you're around a dense area, everything is like together dense, the energy will be low. Energy is like an amount of movement that you can, for example, have. As you get away, you go toward the more sparse region, then the energy becomes high. That's why we use a negative of the energy. They have a reverse relationship. The energy and the value that your model has, the f of theta. So does that make sense? So it's possible in the book or in the slide, instead of f, you might see e. The only relationship, the difference is that one is the negative of the other one. Okay. So
Is there any significance for that transition, like adding a negative and making any?
well, the reason you add a negative technically is here you apply exponential over likelihood, for example. So this is an exponential function. So what happens here is that if the probability, let's say the value, if you have probability, goes to 1, this becomes large, right? If you go to exponential, if you don't have a negative, by default, exponential and function and energy, the density and energy, they have a reverse relationship. That means by default, when this is high, the other one is low, right? So this, you technically need to ensure that you want this relationship to be similar. So you have this negative to become exponential of the negative of the value, right? So that you need that.
So it's just a terminology representation, right? Like
there is no difference between for you using this or that, but it's more possible that you see this instead of seeing f of theta. I just want to let you know that just there's a difference between them.
Can I ask a question? What is this energy you're saying? Like, I don't get it. You know, like how I can relate in my mind energy to this probability. It's a little bit out of nowhere. No, because, and I know this is out of discussion of this class, but the thing that you said over there makes sense that when the probability is high, energy should be like, let's assume that the probability is the molecules that you brought it up, right? More vibration, more movement, more energy. Like
No. So yeah, okay, yeah. We're not going to go that far. But what we are basically here saying is that when you're in a denser region, okay, the energy is not. This is not about the molecules. The energy of that function is going to be lower. It's reverse energy. It's reverse relationship. Okay, this idea is taken from the thermodynamic. It's taken from thermodynamic. Okay, now why we call it energy? I mean, you can call it whatever you like, but the idea is that we want to ensure that whatever we predict for a higher likelihood, if the data is more likely, we want that value to be higher, and if your data is less likely, you want the value is being lower. Right, and because this maps again to thermodynamic, we use the term energy, but you can just imagine that's F, right? So now, bear with me. We'll get to. We will expand it more. Okay, just bear with me. Now, why we use exponential? Why we are not just putting in a square value, and those are just. To capture the variation, larger variation, to connect it to exponential families. It just has some roots in statistical physics. So these are some reasons why here we have an exponential and not f squared. Okay, so it's just for simplicity. Then for f of theta could be technically any function. Is your neural network, is your model, right? So you can just imagine your f of theta is the model that you have. Parameterized by theta. Okay, so the problem is that sampling from p of theta, is not easy. Well, it's never easy, right? It's always challenging. We have a problem with the high dimension distributions. This goes back to the previous class. I think if we asked the same question, when you go to higher dimensional data, sampling becomes really hard. Because when you in a high dimension, when you sample, is actually if you ask the model what's the likelihood of this data, is always really small. Could be even closer to 0. So this makes it really challenging for sampling. The other problem is that this z theta is an integration over all possibility itself. So itself is intractable. Okay? It's going to be really hard to find z of theta, the normalization term. So the idea is cool, but it's not that easy to calculate. Okay, so as you see, there's one pros, and then there are like a series of cons, right? So evaluating the likelihood is hard. There is no feature learning in general form of this energy-based model. And then again, curse of dimensionality itself, which is another problem. So by default, in a vanilla form, this energy-based, the idea makes sense, but it's not as easy to generate this type of model. Now, think about this. If you're trying to compare two tasks, like let's say I have or two images, okay, and you have image one and you have image two, and then for both images, you try to pass the image to this function divided by this, okay, and then you pass another image to this function, like two images. You want to see which one of them is more likely. The idea here is that despite the fact that we need this z of theta, if I look at the problem differently, if I try to look at the problem and say that which one of these two images is more likely, I don't need that. I can find the ratio of this divided by the value for the other one, right? So you technically don't need this z of theta if you are trying to answer a question like which one of these two images is more likely. So that's where the z of theta disappears, and you can just calculate the pair of theta for this one becomes technically the exponential of this value minus the other value. So, so again, if you try to just compare data and see that which one are more likely, you don't need the normalization factor. All you need is some exponential over the model value and the difference between those two. Now, and there's like an example here. If you have a object recognition, sequence labeling, image restoration, all of this basically, E here stands for, could be the same that we just talked about, like the energy that you have. Or think about your model, like expert also you can look at it like that. You might not actually need Z for answering these types of questions. You know, you might need Z for seeing if the data is likely, but maybe you don't need Z to answer a certain question. Or if you're trying to resort the email, like you have an image and you try to improve the image, maybe you actually don't need the Z value for that. And that comes also back to another types of model called Ising model. That's we use this Ising model for denoising. So what you have this image, by default it had noise, and your idea is that to denoise it. Okay, so you can think about this like a Markov random field. And the idea of Markov random field is that, so if you have, first thing about Markov random field is that you have a data set that you can write it in sort of graph mode, where the nodes in the graph, they have Markov properties. Right? That means only depends, like a kind of like they only depends on the previous nodes. You don't depend on the rest of the nodes, right? So, and it should be like a unidirection. So the idea here is that, well, you have a real data point, like a real pixel for an image, and you have a noisy version of the same pixel. So you have this for all the pixels. And in this types of model, you're going to answer this question: what is the probability, like a joint distribution between noisy image and a real image? And you can basically calculate this normalized by Z. And what you see in the formula here, there are two pieces, left and right. The piece on the left is pixel-wise comparison between real pixel and the noise pixel. So Y is a noisy pixel, real pixel, sorry, X is a noisy pixel. So pixel-wise comparison between a real pixel and noisy pixel. And this function, technically what it tells you is that if you use the noisy pixel instead of real one, how good the noisy pixel describes the real pixel. That's this function on the left. Then you have on the right, okay? The term on the right is across all pixels in the real image without the noise. So it looks at the relationship. So I and J belong to the neighborhood. That means if you have this, like these are some real pixels, when it says E, like I and J belonging to E. That means if you are trying to check this pixel, you look at the neighborhood of this pixel, all the pixels in your neighborhood, and you compare those pixels with the current pixel that you're at. So this term basically tells you that for a given pixel, if you compare it with the neighboring pixels, how similar they are. Okay, so this is the second term, and that's the first term. So first term compares the actual pixel with the noisy pixels. The second term only focuses on the real image and says that how similar the pixels, the neighboring pixels in the real image to each other. Okay, that's the idea here for async model. We train this type of model to denoise the image. So we don't want to focus on the async model because this is just an example. Now, all right. So to train this, just to summarize, we need that Z. But what basically we are saying here is that if we try to just maximize this term, I think the solution for that is also in the slides that you have. The Z term will cancel out. So that's again another proof that for these examples, you actually don't need that Z. It will basically cancel out if you try to solve it. So that Z term that you see over there, it will cancel out itself. Now, another example is basically like a product of experts. When you have series of expert models and you want to combine those. Now, if you think about this, there are a couple of ways that you can combine basically expert model. It could be like the AND concept, right? And it could be the OR concept. So it's going to be conjunction, disjunction, negation, right? So there are these three ways that you can basically combine those. Now, if you think about this is a simple scenario. I have three expert model, one of them P theta 1, the other one Q theta 2, and the other one R theta 3. So there are three expert models. Let's think about I built three generative models and I'm trying to combine those. In order to combine those for the same data, you pass the data to individual of those. Each one of those gives you some probability. How probable is this data? You multiply the probabilities together. The problem with that is because they're coming from different models, there's no guarantee that sum to 1. So you need to normalize it. So we normalize it by this term, which is normalization of this across all three models. So that becomes the mixture of the models. Now, let's look at this example. So you have this image processing, image generation models. The one on the top, it's basically focused on males. The one on the left focused on wavy hair. The one on the right focused on smiling. Depending on what you are trying to do, it's going to be conjunction, disjunction, or basically negation. You can basically go on this Venn diagram, figure out which region you will get. And that's how you can combine these basically models. Okay, so if you're trying to do or, it becomes all of this. And basically you combine this the way that you saw. And if you try to do and, depending on if across all of this, then that's the only thing you're going to get from these models, right? So this is just an example of how you can combine these models. Now, the overall idea is that as we go through is for this like an energy-based model, you have training and you have sampling. There are two different things. On the left image, there are two parts: single noise level, all noise level. Single noise level is a scenario like, so the black line that you see, the black curve, is the true distribution. And what we will see, and as we go through this, is that when you pick data from the true distribution, especially in a high dimension, the likelihood is always close to 0. It becomes less likely, even if data comes from the distribution. The idea will be that if we add noise to the data, to the real data, we kind of like smooth out the distribution. So instead of the real distribution is kind of like concentrated. When you go to higher dimension, the chance of falling to that region is really low. What we do, we keep adding noise to the data that kind of like expand the distribution. So it makes it more likely for a point to have a probability value. So in this, on the left, if you add one basically noise level, that means data could be generated from this region, the yellow, or you could have multiple noise levels. So during the training, we keep adding noise, and we will learn this as we go through the slides. We keep adding noise, and we train the model. The model will learn that, okay, this is the real data. You added a noise, and he learns how to denoise it. I'm going to focus on that. By denoising it, the model learns the noise and will learn the black curve. Instead of we just focus on the black curve, we focus on a noisy version to solve it from there. When you do that, when you have that model, during the image generation, or basically the testing, so any of this image that you see, there's an arrow to another image. The arrow points toward the actual image from a noisy version of it. So during image generation, you pass this noise, like this is something that's not easily readable, to the model, and tell to the model, remove the noise from it. Because the model learned that during the training. Then model will produce this one. So that's the idea. If you, during the training, you keep adding noise to the data, different noise levels, and teach to the model how to get rid of that noise, because I have the real image also. During the testing image generation, you can pass a noise to the model and say that build an image from that. All right, so it kind of becomes the idea. Now, the next one, as just the fifth example, is going to be RBM, restricted Boltzmann machines. So RBMs are actually one of the early generative models. The idea of RBM is that, so you have two types of variable, X and latent variables. There's this equation. So there's a W weights of the model. There's a bias for the X and bias for the latents. And this is the value that you're generating. You put an exponential and divide it by Z to ensure that's normalized. Why we call it restricted machine? The restricted Boltzmann machine, the reason it's restricted is there is no interconnection between nodes in the layers. Nodes are only connected to the next layers. There is no connection within layer. It's restricted. So they are restricted from sharing information internally. They can only share the information externally. Okay, so that's why it becomes restricted machine. Now, in one thing that we do, and that's like a deep restricted model, is that you just stack them on top of each other. So look from bottom up. So here, V is your maybe original data, and H is the hidden layers, or maybe bottom down if the layers like that. But what you notice is that there is no connection laterally. There's no connection between a layer. The connection is only to the next layers from the nodes. Okay, so that's how you stack basically RBMs on top of each other. Now, okay, this is an example of what you can generate with an RBM model. During the training, you pass that to the model, and during the generation, it can generate something like that. Okay, so. Now, the challenge, similar to all other models so far, is that finding that Z is difficult. Because here in RBM especially, in this equation, you have X and you have Z, two variables. So you need to do actually summation over all possible X's, summation over all possible Z in order to find this term. So it becomes pretty computationally expensive, right? It's kind of like, it's not that easy to find. Now, that summarizes what I just talked about. Now, this, what we want to talk about is that the idea of what I said at the beginning of the class. When you increase the probability, the likelihood of a data, a real data or a good example, you need to ensure that your model decreases the likelihood of the rest of those, like the negative samples. So what you see in the curve is like you have this data and you have this f of theta. Correct answer, wrong answer. If the likelihood of the correct answer is low, during the training, our focus is that to pull this up. But we shouldn't only focus on pulling this up because we need to also push this down. Because otherwise the probability would normalize. So the idea of the normalization is that you basically focus on changing the curve this way by pushing one down, pushing one up. So that becomes that's the goal that we have. Now, again, our goal will be to maximize the probability of a data. Probability of data is defined as exponential over the model, the function that you have divided by some normalization term. And normalization term, again, comes from here. Now, if we think we have the next slide. Yeah, so when we try to, let's focus on this one. When you try to find z of theta, just estimating the z of theta, instead of we basically finding it totally, we use Monte Carlo to estimate the z of theta. Monte Carlo, the idea is that we'll sample some points using that samples to find the value of z of theta. The steps that you basically take, one of the steps is that instead of sample from the good data, you actually sample from the bad, like negative samples. So this defines the contrastive divergence algorithm. So we'll come kind of like a negative sampling. So you take some negative samples, you update our theta by taking a derivation with respect to this term, f of theta of sample. So there is a, if you, I think we have, so this, the proof of this comes into the next slide. Let's actually first start with that, sorry, and then we go back on this one. So look at the term that we have here. So we have E of this divided by Z, and this is equal to probability of data X, correct? But how likely is a data point? So what we do, we apply log to this, and you apply the log here. The log of subtraction becomes log of, log of division becomes log of subtraction. Then you apply the derivative, because your goal is that I want to find this theta anyway. That's the idea. So you take a derivation with respect to theta. So that you have this first term. Actually, let's write it. So we have log p theta x becomes log of that term. So the first term comes out is technically exponential of f theta x minus log z theta, right? So the log and e, they cancel each other. So in the first term, you see it's just f theta extreme minus log of this. Okay, so that's the first one. Now, what we say is that your goal is to maximize that term because that's maximizing the likelihood with respect to what parameter? With respect to theta, right? So how do you maximize it? Take a derivation with respect to theta. So if we take a derivation with respect to theta, technically you have this term minus gradient of log z theta, right? So that becomes the this term. Now, about this term, gradient of log z theta, this term could be written as basically a gradient of z theta. So if you think about it as a log, becomes 1 over, right? So this becomes gradient of log z theta. So, or reverse. What do we have over there? We have gradient of log z theta. Yeah, sorry, the gradient is behind. So log z theta, gradient of log z theta. So, or gradient of theta, sorry. Pick this, replace it with this one, and this term basically comes out. Okay. And the reason, so let's do this. So we have this term, f theta or f theta x minus, this term comes out z theta gradient of d theta over z theta. This is the second term minus that. About z theta, what we know is an integration over all possibilities. So that's the z theta. That's the z theta. And then this here also this is z theta. So you basically, if you think about z theta and you apply the gradient to it, you can take the gradient inside the integration. So that's what you see here. So z theta is exponential of this times that integration, right? Yeah. Do you remember that from previous slide?
Yeah, but this is why the gradient, yes, gradient can go into the integration, but there is a function of theta before the gradient. It cannot pass that exponential. Either
Why not?
because the exponential of f of theta of x is a parameter of theta, and we are taking the gradient based on theta.
This is a constant. F of theta is, it just gives you a value here, right? And if you think about exponential, when you have expected value, when you have summation px, let's say summation px p theta x dx, we have something like that. When we apply log, we didn't apply log here. We applied the log in here because you're for this term, right? The second term. One of them is the probability, is like a weighted averaging. The first term, this exponential times the function. It's kind of you just doing a weighted average across all values. So when you apply the gradient, you would use the gradient on the function, not the weight that you have multiplied by.
Could you go back to the previous slide? What
Yes.
the original function was?
This one?
Yeah. That's like exponential of gradient. So it is e power x, e of x into gradient of f of x.
Which for the gradients?
Yeah.
Yeah. So if you take a gradient of this,
Oh, yeah, that is z theta.
all right. So anyway, so go back here. So we expanded the z theta part, and then you have a z theta on the denominator. What we can see here is that this two term. So where were we? Here. So you can write this as a sampling expected value. If I sample a point, calculate this term, because again, this is the constant here, right? So this becomes the final value, becomes the gradient of a function with respect to a training data minus expected value, or this term, over the sample data. Okay, so the first term is with respect to your training data. The second term is with respect to your sample data. Does that make sense? So let me ask this side of the class. Does that make sense? Which part?
Sample. I didn't understand.
Which part? Like, what did you about the sample? Why is a sample?
Yeah.
Okay, so you have two pieces. One piece is that it was from the beginning Z trained. Is with respect to training data. Then you have this part, which is the normalization. What does that normalization tell you? You need some weighted average across all possible data. Correct? What did we say? It's expensive about that calculating z theta across all the points, right? And in the previous slide, what did we say? Instead of make z theta, we sample using Monte Carlo, right? So because z theta becomes intractable, it's really hard to find. So we take a bunch of samples, using this bunch of samples to find z theta. So what will happen here is that becomes two points, an expectation over a sample point, and this term over the original data, like a training data. Does that answer now?
Yeah.
Okay. So we have this final term, which there's a gradient minus expected value of the gradient. Okay. So Now, the first term becomes gradient of the energy for a training point. The second term becomes expected gradient for the distribution. Okay, so you're comparing for a given data point, the gradient of the basic energy for that data point and compared to the gradient across the entire distribution. And that basically the unbiased estimate you can, for one data point, it could look like this. So if you only have one sample data point, the previous formula, this one, is the expected value across bunch of samples. But what if I only have one sample? Then you don't have expectation, get rid of the expectation term, you just have one value. So you have two data points here, what it says. I have a real image, the X-ray, and also I have a sample. Because you only have one sample, there's no expectation anymore. So that expectation disappears because it's only for a single sample. Gradient of the energy function for a data point from your training minus the gradient of that function for data point from your sampling. That becomes your goal is to minimize this too. Okay, so the next example basically comes from this distribution that we just saw. Now, the challenge that all of here is that, well, that sampling itself is not a straightforward thing. We keep saying sampling, how we want to sample, like where should we sample? Because if you think about sampling and this distribution, where from this distribution you want sample and how you want to sample. That itself is not straightforward. Now, there are a couple of sampling techniques that we're going to go over. The first one is going to be MCMC, and that's Markov chain Monte Carlo sampling. The idea here is that you pick some point randomly, then at any point, you add a noise to the data point that you have. So because you remember during the training, the idea is that you have a real data, you keep adding noise to it, and you learn to denoise it. So you need to add noise. But the question here is that, well, can I add just any noise? Or as part of sampling, that's the sampling, right? Can I just add any noise or no, it should be some criteria. In MCMC, basically, we have some criteria. So for a given data point, real data point, X0, you have a loop. You start by adding a noise. Previous version of it plus some noise. Then you check if the value, the energy value for the current version, the noisy version, correct, is better than the energy value of the previous noisy version, I accept the new noise. That means that you slowly adding noise to the model, to the data, but you need to also have some condition to see that if the noise that you added, it was in a good direction or in a bad direction. So if the noise, the energy function for a new noise is better than the previous one, you accept it. If not, and this comes back to the idea of like if you think in the reinforcement learning, exploration versus exploitation. Here we say that if it's better, we do that. That's exploitation. In the second one, we say else. And this else becomes kind of like exploration. We need to technically reject it, but we say instead of just rejecting it, we actually accept it with a probability. Otherwise, we reject it. So we have a chance still to try something new. And we will say that this is within the else. Else, we will accept this if with the probability of minimum of 1 and this term. Okay, that becomes so this for a proposed sample with a new noise, the energy of that minus the energy of the previous noise, you find that gap, pass it to an exponential, and between 1 and that term, you pick the one which is minimum. With that probability, you accept it. Otherwise, you reject that sample and continue. Because that becomes the exploration part of the process. So you keep repeating this process and you're just adding noise with the idea of during the training to add noise to be able to denoise it. The drawback of this is that it takes a long time to actually work. So this like a MCMC in reality is actually pretty slow. So there is a second version, or basically kind of like an improvement here, and that's like an adjusted Langevin MCMC. Okay? So in this scenario of the MCMC, what we do, we basically start with an image again. This is during the training, okay? So, and then for a couple of timestamps, you add noise. How do you add noise? You generate a random Gaussian value, Z, okay? And then you update your basically perturbed data as the previous version of it plus this term, okay? So here Z is the just Gaussian, and epsilon is, for example, could be some it's like a hyperparameter that you are adding. And then you say that I will accept this perturbed version with this probability. Okay, that's a Langevin MCMC. So you're basically ensuring that it's the noise that you're adding is a good noise here. That's the idea. Now, there are some properties with the Langevin MCMC. This guarantees to converge if you keep sampling and you're reducing that epsilon. As epsilon goes down and the number of samples that you have goes up, it's basically converge. That's guaranteed to converge. And then what we basically also see that for continuous models, this term, gradient of this f theta x, is going to be the same thing. That means the second part is disappearing. Okay, so if you, using this technique, unadjusted MCMC, as t increases and epsilon decreases, one of the properties that also you have is that the gradient of the log that you have, this term, the gradient of the density value, the gradient of that is guaranteed to be the gradient of this, that disappears. Okay, so that's a property that it has. Now, limitation to it is that it's still slow. Okay, so it's kind of like has some issues. Now, first up, any question on that?
So can you please go 2 slides back?
2 slides.
33, yeah.
This one?
Yes. So we here in 2.3 we're saying we choose we accept the xt plus 1 with the probability of minimum of this, right? So my question is, it's minimum of 2 probabilities, right? But if theta is not normalized, that's why we added z theta in the first place. So how can we take the difference of that and compare it with the probability of 1? And
so remember we talked about that. Not for every point you need that z theta. For comparison of 2 things, this is technically exponential of this minus that was the one divided by the other one. So if you do exponential of f theta 1x over z theta divided by exponential of actually f theta x1 or f x1 divided by f theta 2x divided by z theta, you technically don't need the z theta, so that term comes out. Right? So you need z theta for certain things, but if you try to compare 2 samples to each other, you actually don't need the z theta. Okay. So now, all of this technique, they are basically working based on sampling, and sampling is slow and it's challenging. The idea here is that could we do this, basically, could we solve this problem without sampling, without a need to actually sample real data? And that's the answer is that yes, and we're going to talk about something called score matching, noise contrastive estimation, and adversarial training. These are the type of technique that you can use to get rid of that sampling concept. Now, so let's just start here. So if you're looking at the image on the left, what you see is the probability density. So the probability density, like you have a high peak here, you have another peak here. If you take a derivation of basically that probability density with respect to points that you have, with respect to data x, what you will get is the one on the right. So this is the gradient of this with respect to points. Okay, so what we are basically here saying is that, and we are trying to solve this problem, and this was exponential of the function, the model that we have normalized by z. We also say that this log, if you apply log to this, becomes this term, which is makes sense. If you apply log to this one, becomes the one on the right. And now we're going to talk about something called a Stein score function. The score function basically says that there is our goal is that to find this. Okay, this theta, we want to find that. Could we estimate it using another neural network? That's the idea. Could we estimate this gradient using a model? And that's where this score function comes. So there is a S theta, a model that can approximate this. This is equal to gradient of the function. So these are all the same term. Okay, just for you to see that. So your function is, the original function is f theta. If you take a derivation of f theta with respect to x, is the same as taking a derivation of log probability of theta. Okay, which is this one. Those are challenging to find because you don't have P of data technically. So you can't find that. So the idea is that could we estimate, approximate it using something else? And then that's where the score function comes. This S theta is supposed to approximate that for us. It's almost equal. Now, so this, yeah.
Question. This is why we need even the gradient with respect to x.
We're going to do right now, go on that in the next slide.
One is, and second is that s theta shouldn't be, for example, s something else. Because if we say it's a network.
You mean the parameter?
Yeah.
Oh, yeah, yeah, that's correct. It could be, it could be a function of we write it actually with respect to theta because we approximate that. That's terminology. So now to go back to your first question, he's like, well, that's a great point. It's like, why we take a derivation with respect to data? We normally take a derivation with respect to parameters. So think about one thing. Anytime you take gradient with respect to a parameter, what does that gradient tell you? With respect to w theta of a function, what does it tell you?
A little change in that parameter make how much change in what
Model
the
out.
words is.
Right? If you take a derivation with respect to data, now what does it tell you?
How sensitive it is to data.
How change the data?
How sensitive is to change to the data? If I perturb, add some noise to my data, what will happen? By focusing on that, instead of focusing on the parameter, we learn to see that how likely an image to be real based on the gradient of the model with respect to a data. And that's where comes to this, which is called vector field of gradients. So think about, so on top you have a Gaussian distribution. This is the normalized function, energy function, normalized version. If you take a derivation of this with respect to x, this term becomes the score function. So this is called the score function. If you have a gamma distribution, this is called the score function of the gamma. Derivation of that with respect to x. Now, let's assume, to understand the image, let's assume you have mixture of Gaussian. You have two Gaussians technically together. On right corner, on the left corner. So unfortunately, the color is not that obvious. So what you will see, there are some basic lines, like contour lines as you go. What you see in the image technically is there is a region here, there is a region here, two mixture of Gaussian. And as you get away, basically, technically, it's kind of like this. Right? You get away from the center of those Gaussians. Now, the contour lines, it basically tells you that the probability levels. That's the contour lines. The arrows are the gradient of the basically function with respect to the data. What does it tell you? Long arrows tells you that you need to go a lot. you are so far from high density region. Small arrows tells you what? You are close to high density region. Why we care about? If your goal is to generate image, you want it to generate it from high density region, like it's like being able to realistic image. So by focusing on seeing that how should I perturb the data? Now think about the idea of noising. You add a lot of noise, or you start from noise, and you start removing noise based on how this arrows tells you to go. And the arrows basically, this theta we learn it over the training data. After we learned it, if I bring in just an image of all noise and say that, okay, tell me which direction to go. These arrows tell me which direction to go to convert that noise to an actual image. Okay. Is that clear? So that's the idea of this score function, and this basically a score function. Our score function methods are focusing on this idea of like a vector, basically gradients. You know, it's just a vector field of gradient. So it's not based on maximizing likelihood and stuff like that. It's just focusing on this vector gradients. Now, this vector field or vector field of gradients, basically that's the definition. But one thing that here ought to remember is that all of these things that we have seen so far, basically energy-based model, autoregressive flow model, these are all energy-based and these are all score-based. Okay, so score-based is actually a bigger family that covers all of those. And then it's energy-based and it's autoregressive and it's flow. You can actually, if you think about the autoregressive or flow models, one thing we saw at the beginning of the class is, if I just go back, that's the flow model and that's autoregressive, right? By default, it's guaranteed autoregressive models. This is a valid distribution. And this is a valid distribution. This term made it valid, remember? So if you think about z theta equal to 1, instead of z theta put 1, now this is a energy-based function. Now for this one, put it divided by z theta and set z theta to be 1. Now that's a energy-based function, right? So it is not actually an energy-based function, and by nature they are basically normalized. Okay, so now what is the goal when it comes to a score function? The goal is that we want to use an S theta, a model, to approximate that. Because we say that we don't know p theta, then so finding that actual gradient field of p theta is not easy. So let's find a model that model predicts a score that actual gradient field should produce. So instead of you actually having that produce that gradient direction and magnitude, can we estimate it using a model? So that's what we basically want to do. We want to approximate that. Now, we in order to solve this problem, now we think about this. We are approximating that gradient field from the real data with something else. We need a way to see if this approximation is good or bad. There is a divergence called Fisher divergence. So if you have a P and Q to distribution, the Fisher divergence basically becomes this term, or a P and Q. Okay, so gradient of log P minus gradient of log Q, norm 2. That's called Fisher divergence. So we're going to use the Fisher divergence because it's also based on the gradient for comparing the S theta, the approximation, with the original log P data, the one that we actually see that it's hard to find. So our goal will be that to minimize this divergence, basically. Okay, so our goal is to be sure that you're closer to each other, our approximation. Now, these three equations that you see, they're identical. I put those on purpose to tell you that if you see this is the same as this term. This is the same as this term. These three terms are the same thing. So S theta is defined as gradient of F theta x. That's also the same as gradient of log P theta of x. Okay, so these are the same term. Okay, don't confuse those. Now, okay, so how could we make this like easier, this problem? What we can do is just expand it. This is this term minus this term norm 2 to the power of 2. It technically means that this one to the power of 2, right? The whole term to the power of 2. Take it to the power of 2. So that's what you see. So basically we will take it to the power of 2. So you have two terms, basically take it to the power of 2. This term comes out, then this term, and then multiplication of those two terms as a negative. Okay, this part makes sense? We just take it, whatever is inside the parentheses, to the power of 2. Now, the challenge, if you're looking at these three terms that we have, the challenge that we have is this gradient of log P data is unknown. That's always the problem. And across all these generative models that we have seen so far, anytime you have a P data is technically unknown because we only have samples. So this term is unknown and it makes it difficult. So let's see if we can get rid of that. Can we basically get rid of this one? Now let's focus on so ignore the first term, ignore the second term. Let's focus on the third term first, which is a P data times gradient of log P data times gradient of whatever function that you have modeled df(x). So what we do, we're going to use integration by part. And one thing for integration by part, we can say that if you have integration of fg, we can write it as fg integration of fg prime, correct? So we're going to use that to basically expand this one. So what we want to do, assume that f is going to be the P data. F prime is going to be log of that, gradient of log of that. This becomes G. And G prime becomes technically that term second order gradient. Okay. We might have that actually. Yes, yeah. So just digest that for a second. Yeah.
Just give us
Yeah, go ahead. Everyone good? All right. So now we want to apply that to the third term. So this was the third term here. Okay. One thing here is that if you look at the second term within that term, this is the gradient of log. So we have gradient of log P data x, right? Which, because this is a log and gradient, so you have P, like a gradient of P data x over P data, correct? So pick this term and put it inside the equation instead of this. P data and P data in the denominator, they cancel each other to end up with gradient of x P data, gradient of f P data. Okay, so that's how the P data disappeared. Now, so there was a negative also behind it. So basically, this is what we have right now. And what do we see in this term? This was f prime, right? We just showed it in the previous slide. The first term, gradient of x log P data, it's the f prime. This one is this one, f prime. And the G is gradient of x f theta. Right, this was in the previous slide. Look at the f prime and G. So now we have that integration by part, integration of f prime G. We can write it as fg minus integration of f g prime. And g prime becomes second order derivation of the same thing. So that's how this term will convert to this term. The first part of the integration by part and the second part. The first part of the integration by part goes to 0. Why it goes to 0? And this comes back around about the same thing we just talked about before. What you see, there is a interval, minus infinite plus infinite. And that's where the data value comes from. As the data becomes larger and larger, basically, in a higher dimension, what do you think happens to the probability of data x? It goes to 0. So that across all possibilities, this term actually goes to 0. Because that p of data becomes almost 0. And that multiplication goes to 0. So the first term is ended up being 0, because again, you need it for across all possibilities. So this is the only term that comes out. P data x is second order or Hessian of your matrix or your function. So this becomes the third term in this equation that we have. Now let's replace it. So we will have, what did we have here? 1 over 2, 1 over 2. Yeah, okay. So we have these 3 terms. The first one was basically this one. The second one was this one. And then we just found this third one. Now, if you look at the first one, which is the only one that we still need that gradient of log p data. Okay. With respect to theta, because we're solving for theta, this is constant, right? This doesn't have the theta for you. So with respect to theta, that's constant. So we don't need to focus on that, despite the fact we don't have the gradient log p data, but because it's constant with respect to theta, what we solve for, so we can just write it as constant, ignore it. So then you have this term plus this term. And these 2 terms, they have one thing in common, p data x. So you can write that as, because if you think about this, this is the expected value of this term with respect to sample from p data. This is expected value of this term with respect to sample from p data. So the total becomes expected value of this plus that. If I sample from p data, my real training data. Question on that?
A bit confused, like,
Which part?
go back to and we rewrote the integrand,
Okay,
and then so in the end the integrand was,
that value at the end.
yeah, it was like what do you say, the p data x and like on top, yeah, that term to, how did that log come back in that term again?
No, so the log is not coming back. I just say that this was the original term. I rewrote it. This is not this converted to log.
Confused.
Well, which part? Maybe I'm not getting your question. Oh, I see. So this should be a typo then. There's no log here.
Right.
Yeah, that term should be negative. I see what you're saying. There's no log behind p of data. Yeah, so it doesn't exist here either. Okay, good catch. Yeah.
Now, one more doubt in this slide only. P data of x multiplied by the gradient
Mhm.
across all the possibilities. Doesn't that make it an expectation? And then why it is 0?
Because
Summation.
when x goes toward infinite, what does that mean? When x goes toward tail of the distribution.
Summation, oh, sorry.
There's
Oh,
no summation.
shit, I'm still, yeah, yeah.
Yeah.
I'm
It's
thinking
like
in
those,
terms
but when you go
of-
toward the end of the distribution, the P of data goes to 0. All right, so. Okay, so the first term was constant, and then this one, we can write it in this form. So it becomes expected value. If I sample from my data, this term plus this term. The first term is basically Jacobian to the power of 2. The second term is a Haitian, right? So if we want to convert it to an error, instead of the Haitian, you can basically put a trace over the Haitian because you want the diagonal values over the Haitian. So that's where the trace comes. So it becomes a square root of gradients plus trace of the Haitian. So now this will become the steps of this model. So far, you have a bunch of data points that comes from the distribution. And your goal is that to estimate that a score matching is theta. And the way that we estimate it is that we use this function, which is with respect to gradient of the function, with respect to data, every data point, and the Haitian of the function. And that's like a trace of Haitian. So let this run and just using gradient descent and update it with respect to theta. Let it run for a series of time, and then you have a model. The challenge is that Haitian. Anytime we have Haitian, it's expensive, right? So because the model requires a Haitian, it's going to be expensive. So we need an alternative way to solve this. Okay. So all right, let's take a break, and then we continue from there. What I wanted to go where was, your friends, they had this question about this idea of the gradient with respect to data and what's the connection to the model, actually, how does that work? So think of this. We are trying to find probability of data for a given data. That's always what we want to answer. How likely is this sample that we have? If it's a good sample, it's like it should be high likely, right? And what was the idea? Well, okay, in order to estimate this, we have this model, F theta. It's a neural network that data goes through it, and at the end, it gives you a probability. If it's a high likely, it gives a high, maybe high value, or low likely, it becomes low value. The problem with this model was there is no guarantee that if for an image, for data is likely, but the rest of them becomes less likely. So what we say, we kind of normalize this model by Z of theta. Okay, so now the idea of a score function is that, well, when we want to update this model, we want to update this model not with respect to focusing on with respect to basically the parameters, just focusing with respect to data. If I pass a data goes through this model and I make a prediction, if it's a real data that should be high likely and the model predicts low likelihood, I use that knowledge to update the model parameters. But how? By taking a derivation of this with respect to the data, not the weights of the models. Because the derivation with respect to the weights that sits on these lines, it tells you that if you change this weight, how much improvement you get on the model output. That's not our goal. Our goal is that how to change data to be more likely. Because you do generation, you do image generation. So you want to be able to pass something to this model to generate something that's highly likely. So we focus on how can I change this model so it basically generates more likely data. That becomes the focus. And that's why we saw in this slides, there was 3 terms on the last one: gradient of log p data, S theta, gradient of F theta. These are like the same terminology. It's basically focusing on changing the parameters or changing the model with respect to gradient of with respect to data. Okay, not the reverse. And that gradient of data, again, it's going to give you this basically gradient vector field, which tells you that if data comes from this high density region, how can I have a random sample but change it somehow so it goes to this region? So if you, what it means is that, let's say I pick a very random sample and it's Gaussian noise. So the likelihood of that should be around here, somewhere here, because it's not possible. It's like a less likely. It's totally noise. The idea will be that which direction should I go? If let's say here this is a class cat, this is class dog. I want to generate an image of cat. Which direction should I perturb this noisy, like a denoise, this image, in order to generate a cat? So this vector field tells you which direction to update, to go towards. You use that knowledge to iteratively remove noise, denoise the data until you get to the point that you have the image. Is that clear? Okay.
Till now, that's just a discriminator function, right? That's it, like it doesn't have the generator capabilities yet. But let's say we are passing X and we are getting a score out of it.
No, so it depends on how you look at this. First thing is that there are two steps. During the training, your goal is to find the score function.
Yes.
That's during the training. After you're done, you use the score function to denoise.
Yes.
So that what I just example that I went over, like imagine you have a noise there, that's the denoising during the generation. This is during the training. Basically, to find it, you use it. During the training, basically, you try to estimate S theta. But during the generation, we're going to also go there. During the generation, you still use this like a gradient of S theta, because that's how you can guide the noise to go to a certain direction. What was that?
A real picture.
That's correct. So if I had, no, so let's say I have a total noise. This is done. I have this F theta or S theta done, trained during the training. A score function is trained. Now I have a noise. This is just noise. It goes to this model, right? What I want to do is that I want to denoise. How do I denoise? I take the derivation of this with respect to the noisy image, X. That tell me which direction you need to go, because the model is already trained. It tells you that the model, so S theta, what does it estimate for us, S theta, or S function? It tries to estimate the gradient of log P data. P theta, sorry. They're estimating this one. If I have learned this already, the S theta during training, during the generation, I pass an image and I say that, okay, I have S theta. Tell me which direction should I change this image so your score is higher. If S theta has a high score as a prediction, high score means what? Means in the vector field means you are in the region on the two corners, right? So if you are in these two regions, two modalities, you get a higher score. Your gradient becomes small. If you are here, the score is low. You're far, your gradient becomes large. So if I have a noisy image, all I need to do is that pass it to the score function, see how is the score, see the gradient. Gradient tells me that if you need to, how far you are from good answer. Keep iteratively move around this direction until I get to the point that the score is high, or basically the gradient of the score is low.
So one thing, it's not like in the generation phase, we pass a noise and the network denoise it in one round.
No, iteratively.
It's iterative.
We're going to right now go over that. We haven't talked about it. It's iterative denoising process. Okay. So all right. So Okay, so just quickly recap. We talked about this idea of score matching, score functions, and let's go here. So let's start from left sample, left image. You have P data. This is the original distribution, right? Which is most of the time unknown. So you have two modality. One is highly possible, the other one is less possible, like kind of less likely. If you sample, some sample comes from this region, lots of samples comes from this region. Our goal is that, because we don't have the P of data to basically to learn this vector field from it, our goal is that to estimate this vector field using a function, a score function. So the score function is going to estimate this that we couldn't find because we don't have actual P data. Is that clear so far? So that's the idea of the score function. Then you can, then we say that we're doing a score matching, and that becomes like the Fisher divergence, for example. We use the gradient of the real P data minus the gradient of the score function, right? That's how you compare them. And the idea of that basically score matching is something like this. So imagine on top, the black arrows are the actual gradient from the score field. Gradient of log P data, actual, real one. The one on the bottom is the score function that you have. And the blue arrows are the gradients, or basically the gradient vectors that you found using S theta. Our goal is that to compare these two to see how accurate they are. If you simply pick this one and put it on top of each other and find the divergence like a Fisher divergence, that tells you how much off you are across all of these arrows. Does that make sense? So it's just we want to simply compare this. Now, again, the score model, it's some learnable neural network, some model that we use to help us to predict that one. And the idea is that we want to optimize the parameters of that model, those thetas, somehow that whatever a score model predicts is almost as identical to the actual gradient vector field of the P data. Now, so let's go back here. So we basically say that a score matching objective, if we sample from real data, we just simply say the P of gradient, the score, like a score field of the real data minus the score function that we have. We saw in the previous slide that that's basically simplified to this term, the Jacobian plus trace of the Hessian plus some constant. Right? This is what we saw in the previous slide. Now, one thing is important that to distinguish here the score function method is that it's independent of z. We don't need that z theta anymore. In energy-based function, we needed that, which was itself challenging and intractable. So instead of focusing on that, basically we went with a score function which doesn't need z theta anymore. So it makes it easier because now you don't need to learn that intractable basically value. Now, there are some caveats, even if you think like ignore the Hessian, which is expensive, but even if you look at the Jacobian, this Jacobian itself, it's expensive, again, especially when you go also to a higher dimension, right? So this becomes a bit problematic, is all this Jacobians, Hessians becomes expensive to calculate. Now, the idea becomes here that how could we improve this process, right? So we don't need to calculate that Hessian or the Jacobian, like, or the Hessian, maybe probably is the most expensive one. So that opens the door to this new idea. It's called denoising score matching. And from here, this denoising score matching slowly connects us to the diffusion models. Which are, the idea is like a denoise, basically, to generate sample from noise overall. So there's denoising a score matching. There's that. We have this X sample, all this data that we have, the sampling data, from sample from your real data that you want to use for model development. We what we do, instead of just using example, we add random noise to the example. So now we basically use this noisy version of the data. During the training, your focus becomes from the left side all the way to a score. This is during the training. The output will be the score estimation, the score function that you have. So from here to here becomes during the training. During the generation is where we do that annual language driven sampling. So from a score estimate is generation. Before that is training. During the training, what is the goal? We bring our data, we add noise to it. Why? Because it makes the distribution wider, smoother overall. It doesn't have sharp value, concentrated data. Our goal is during the training to denoise that data, get rid of the noise that you added. So you have the original data, you have a noisy version. Your goal is that being able to guide the model to tell you that how much noise to remove iteratively, for example. And you remove the noise. By doing so, what happens? We learn about the noise. And also think about this. So if log P data is hard to find, instead, if I do log Q data, where this is a noisy data, right? Instead of that, I do this. And I focus on learning this and denoising it. As you denoise it, what do you learn? We don't explicitly trying to learn that, which is difficult. It's kind of like a parameterization trick. We trick it, we change like, we bring a new distribution like a noisy. We said, okay, I want to just get rid of the noise, because when you get rid of the noise, the distribution that you learn will become that one. So that becomes the idea here, to just focus on denoising process. By doing so, and during the denoising, we need a guidance of like how much denoise. And we do that using the score function, which tells us the gradient directions. So we learn the score function and the denoising process in training. After that, during the generation, because you have the score function, you start with a pure noise. Like we will see examples like just pure noise, and using the score function, you try to denoise it, so you will generate an actual image. Okay, and we're going to break this down. So now the idea again will be that, so we introduce this Q distribution for the noisy data. So noisy data is dependent condition on the real data, because you have a real data, you add noise to it, right? So Q is technically Q of noisy data given real data. So that's the image on the left that you see. For a given real point, like let's say x equal to 1, this is the conditional distribution for Q. On the right is the marginal distribution of Q. And what does marginal distribution mean? That if you pick this across all real images, that becomes the marginal. Right? So the red line is the marginal. So we also have this P of X as like, expected value overall. So conditional, marginal. What does the conditional tell you? A noisy image comes from a Gaussian, where the mean of the Gaussian is the actual image, X, real image, and the variance is some sigma to I. So you actually have the actual image, which is the mean, and you just add some noise to it. That becomes a new data. And this becomes the marginal. And as I just mentioned here, it's easier to focus on learning this, the gradient of this in vector field, than focusing on that. But this is easier for us to solve this one. And so I'm going to play that image for you also to see. So what we will do is that we're going to rewrite our Fisher divergence. So technically, you actually will see this term that this one is called explicit divergence. The previous version called implicit divergence. Here, implicit because you actually don't know P of theta. Here is explicit because you actually have the Q of theta. Right? It's like you have this. So this is called explicit divergence. The other one is like implicit divergence. Now, so you just need to rewrite the formula becomes the difference between a score function for the noisy image minus the actual gradient score field of the noisy image. What does this help us to do? Because remember, what is the goal? What we are trying to learn here? S theta. A score function is what we are trying to learn. How do we learn it? We compare a score function, the score function, think about it as like some neural network. So I have this neural network, which it will produce a score value. Okay, and I want to update it to learn it. What's my true standard real label is the gradient of log Q noisy image, because I have that, right? I have this Q distribution. The gradient of this becomes the vector field of that. So what I want to do is that to estimate this using a model. And that's what this error tells you. Our goal will be to minimize this with respect to theta, which is the parameters of that model. By updating that neural network, we want to be able to predict this. Instead of learning that, we learn this. When you do this, this automatically takes us there. We're going to see that. Now, the image, let me play this. So what you will see as we go to, that's the noise level, how much noise you are adding. The pink, the orange is the noisy distribution, the blue is the real distribution. As noise increases, it becomes really different. As noise decreases, you're actually able to match the real distribution. So that becomes the idea of denoising. The more noise you have, the farther away from you are. As you remove noise, decreasing the noise, you will be able to match to the original distribution. So now, so on the left, you have an image. This is like an image and a real image. On the right, we have a noisy version of the same. So X, P of theta, you add some noise to it, becomes Q, and then this becomes noisy version. So instead of working on this, we're going to work with this one, the noisy. So what we want to do, we want to, using a score function, to basically find the score function somehow that this term is minimal. Right, that's what we saw in the previous slide. And this is expected value, just write the integration with respect to Q. Then do the same thing that we did previously. Take this term to the power of 2, so it produces 3 terms. I code them for simplicity. So you have, if you look at the first term here, this is Q. There is no theta here. So this is constant with respect to theta. Similar to what we saw in the previous part of the class. So the first part, the blue is constant with respect to theta. Then this one, you can just rewrite it again as expectation. If I sample point from noisy distribution and calculate this term, the square value of the score function, plus, minus, then we have this term. So we're going to expand this. Similar idea, I think, what we had in the previous part of the class. Just the log gradient of the log becomes 1 over the value times the gradient, and the Q's, they cancel each other. Okay, cancel each other, same thing. You come to this term. Now here, the gradient of Q with respect to X noisy X bar, this term is equal to this term. If I go at the beginning of the slides, here. qx, you see that the second distribution, the marginal, is this term, right? One on the right. So inside the parameters, inside this equation, this line, what do we have? Gradient of q. And q is this term. That's why you see the second integration is added inside the parentheses. Gradient of that term with respect to x. Okay. So we just so same thing, same question that Ashkan had again. The gradient goes for the second term. So you add the second term over the gradient, write it with respect to we have a fool on this one. So move the term inside. Gradient of log q becomes gradient of log divided by basically the q. That q, bring it inside. So you see the term on the bottom? Do it like a cross multiplication. So this, because this is what we have, correct? The one on the bottom is a knowledge we have. It's not something possible. We know this gradient equal to this. So this term equal this times that, right? So bring this term, put it inside the equation. Just, does it make sense?
Yeah.
Bring this term inside. Now, what we get basically is going to be this integration, p data, q data, this term, s data. And this is, you can just assume it as two expectations. Expectation over points that are coming from p data and over points that are coming from q data, noisy data. This term times this term. Okay, so the term has two distribution in it. One is p data, sample from real data. One q, sample from noisy data. So we write it in terms of two expectation at the same time. Okay, then bring this term and add it to the first one that we had. There was a constant plus this minus that, correct? This was from the previous slide. Now, one thing we can say here is that if you, this is just like a playing with terms. We have this one is a square. This one is negative of this times that. Well, the way that we are writing it is that s theta x minus gradient of x log x. So let me just write it. So we have this 1/2 s theta x norm 2, and then we have minus, there's no 1/2, expectation of x and x bar. I'm just going to write it like that. Then we have gradient x log, let's see, q x bar s theta, that's it, sorry, s theta x bar. Okay. Is power of 2 no. Right. So we have this term, right? This is the same as if you had s theta x minus gradient x log q x bar to the power of 2. One term is missing plus that whatever term that's missing. So they will cancel out. So that what you see here on the whiteboard, does it make sense what I'm saying here? So do you agree with this term? This is what we have over there. Now look at this term here, this one, in the parentheses. Let's say we have this term from somewhere, okay? If I take this actually to the power of 2, what do we get? Sorry, there's a 1/2 behind this. We get 1/2 s theta x to the power of 2 plus, and then there's 1/2 behind this also. 1/2 gradient of x log qx to the power of 2 or norm 2, correct? Minus 2 times this times that. Okay, so we have 1 over 2, sure.
1 or 2 outside.
1 over was, yeah, so yeah, just leave the 1 over 2 maybe outside. So we have minus this times that, so s theta x log x log q, this term, correct? So this part is this part, correct? This part is this part. The only term which is missing in order to have this equation is this term. If we had that, we had this equation, correct? So what we do, we still write it in this form minus whatever is missing. That's why what you see is that term to the power of 2 minus whatever is missing from that equation. We just played with terms. Now, what happens here is that there is no theta here. So now this is also a constant. So if there was a constant, there's another constant also. Right? So the only thing remains is s theta minus basically gradient of log q, like a conditional of q with respect to x. Right, so we and those two constants, you just assume they're just constants.
Lagging a bit, but why is the lack of theta? I didn't fully understand why the lack of theta makes that term constant.
So what are you solving it with respect to? What you're optimizing for? All right. Any question? No? All right. So now let's look at before we move forward. In order to solve this problem, you need this term minus this term. S theta, it's kind of like easier for us. Why? Because it's a model. You update it as you go. The second term is not a model. It doesn't have a parameter with respect to theta, right? But what do we know about this? Because this is a gradient with respect to x. What do we know about q? Well, how did we find that gradient of q, like this, conditional of q? We brought a real image. We added a Gaussian noise to it. We got q, right? So if you go at the beginning of the thing, so this, that's a Gaussian noise, right? Remember at first when we defined q, yeah, that's the q on the left. Gaussian with mean x and variance sigma 2i. Correct? That is a PDF. Take a derivation of that PDF with respect to the x. Take a derivation of it. This is what happens. Acid. Yeah. So you're trying to take a derivation of this with respect to x, the noise. This is the PDF for like a univariate Gaussian. Take a derivation with respect to x bar, the noise. The only piece is this one, right? Because there's a log. After you apply log and exponential, they cancel each other. The only piece comes out is this, right? So that's the score, and that comes back at the beginning of the class. I think I just showed you also the score function for Gaussian. Oh, it's the other slide. Score function for Gaussian was x minus the other data point divided by 2 standard deviation. That's the same thing that we have. So the score field, the actual score function is that term for Gaussian. It's important to remember that we want, actually one of the things that we want to do when we select this function is to be sure that we have a function that is analytical solvable. You can actually have a closed form solution. You can actually take a derivation, solve it. If you pick a type of function that is not solvable, then you have problems. You want to be sure that there's an analytical solution to the function that you picked. That's why Gaussian is pretty good. It has a closed form solution, right? So the second term in the parenthesis in the equation, which becomes this term in the bottom, this is also famous as a 2D formula. Okay, so this is the gradient term. Replace it back into the function that we had. So replace this with what we found from 2D formula, which is a gradient of a Gaussian. So what we end up is that in order to find this error, the error is simply average over points, the score of our model minus this term, right? What do you think let's understand it. What do you think the second term is telling you if you're looking at the term?
Standardization, kind of.
How much is noise is away from the real data?
X is noisy data, X tilde is noisy, X is data. How much noise? Basically, this tells you how much noise you found divided by standard deviation, right? So the term on the right tells you how much noise exists. The term on the left is the score function. You want these two to be similar. What we are trying to do with the score function? Denoising. So the idea here is that to a score function to predict how much noise, because you want this to be the same. So you train a model that it can tell you how much noise is there, how much to remove in order for the image to be realistic. All right? So that becomes the idea. Is that clear? You don't have a question, Ashkan?
Go back one slide.
Yeah.
The gradient is negative, right? So that means when you replace it, it will become positive. Like the sign will become plus.
It's just the opposite direction you go.
Interpretation.
What do you mean?
The gradient is minus of x bar minus x.
But how do you know this minus that is negative? The sign of this might be reversed, right? Okay, so
Here it should be positive. The sign should be positive, right? Plus
let me
s
see.
theta of
So over there we have x bar minus that. Here we x minus that. Yeah, okay. So and why should be?
negative of negative, positive.
Let me see. So in the
Get it.
original one, what did we have? We have
Negative.
negative. We have negative.
Should become positive.
Yeah, so that we should. Yeah, that over here it should be positive.
Yeah.
That's a good catch. Okay, yeah. So the inside inside that should be a plus, I think. After. Yeah. Okay. So this becomes the loss function. And what does this loss function tells you that if you think of the yellow line as the original, real data, and all the red one are the noisy data, it tells you that which direction improve that, so the point will fall on the real data. Because if the point is on the real data line, it has a high density, high probability density value. That means the gradients become smaller now because you're on the dense region. When you are farther, your gradient is larger. The arrows indicates the gradient. So by moving in that direction, you try to go from noisy data to a data that lies on the line where the gradient becomes small. That's the idea here we have. Now, okay, so summarizing the intuition, the score model learns to predict the gradient of this log for the perturbed data. The gradient basically tells you that how we should go back from noise to real, basically real data, like how to transform it. Our goal is that to minimize the gap between the score that we have and the actual gradient vector field. And we solve this model with respect to theta parameters that we have, parameters of the score model that we have. So we try to optimize for that because the difference, the cost function is over there, right? The only part has theta is theta. Now, let's look at this. So as the image on the top is similar to what you saw before, which shows that as you add noise, how far you get from the distribution. The image on the bottom shows you two things. I'm going to play. S theta is the vector field of the blue one, is the vector field of the real data. The orange one is the vector field of the noisy data. And there's the gradient. What you will see is that as we basically these are like a really similar. So even when you add the noise to the data, the vector field is still is pretty similar between these two. So if you're looking at the line that's moving, depending on the direction it goes, that gradient arrow is changing. So what's going on? When you are getting close to the region of high density, okay, the arrow basically tells you that go to this way, go this way. How far you are, the length of the arrow becomes longer. If you are so far, one second. If you're so far from here, you see the arrow is large. As you get closer to the, as you denoise and you get closer to this region, the gradient becomes smaller. As you get far, the gradient, depending also on which modality you're approaching, the arrow will change. Here, the idea is that you have two modalities. What you will see on the bottom is the actual, like the value of the gradient. Goes to 0 when you are on actual modality, there is no gradient. If you're on the left side of the gradient, here on the left side, here we have a basically negative gradient. If you're on this side, you have a positive, then you have negative gradient, like the arrow basically tells you which direction to go. So this is basically what the vector field tells you, which direction to denoise in order to improve, to get to a higher density region of the distribution. So now, to just wrap all of this, okay, why this denoising idea works is we say that finding that log gradient of this, like a square field of the real data, it's challenging because we don't have real data. Most of the time, it's just samples. So the idea will be that this kind of like it has a similar flavor of what we saw in the reparameterization trick in VAE. Instead of sampling from distribution, we introduce this deterministic node, so we can just back propagate through that. Here, instead of having the real image, we create a version of it, which is kind of like a noisy by adding a deterministic, like that has a deterministic formula, not the deterministic noise. The noise is stochastic over there. But what we do, we focus on learning this. As you learn this one, what we learn here is that when the standard deviation goes towards 0, these two become the same thing. So as we learn this, slowly this will converge to the score field of the real data, which is unknown. So we explicitly solve for gradient vector field of noisy data. We implicitly learn the gradient vector field of the real data. That becomes what basically how this works. So there are two quick differences. So we saw the basically normal score matching, and we saw the denoising score matching. The challenge was that in normal score matching, there was, remember, it was 1/2 Jacobian plus trace of Hessian. The trace of Hessian has become super expensive. We say that, well, could we get rid of that? We don't have a way to not needing that. The idea was that, yes, let's, instead of learning the actual data, let's learn a noisy version of the data. And let's just focus on denoising. By doing so, we don't have that Hessian anymore. And the only thing we have is just one Jacobian. Right? It's the gradient of the vector field. It's like so that becomes much cheaper. And then this becomes the 2D formula. So this here is the negative is gone because it's reverse, x minus x bar. Over there was x bar minus x. So on the bottom, this technically actually is the 3D formula. In order to generate a real image, real image equal noisy image plus this value. And this value is the gradient of basically the square field, gradient vector field, times the square, times the variance. This plus that becomes that. Because this will be gradient in which direction to go there. It's like it becomes the opposite direction. If you're on the left, tells you go right. If you're on the right, tells you go left. So it always goes to the negative direction. So this, when you add it to the noise, it denoise basically goes back to the real data. Okay. So now, what you will see here is in this image is that we have 3 images. These are noisy. We have added some noise to this. And our idea is that to push this up to go to a higher density region. And what you see here is becomes that the gradient vector field or the gradient of the a score function. What you will see for this image in this point, at this point it's supposed to be 0 because it's maximum. So if you're on the left, you are here. It's positive, correct? The gradient is positive. But so the gradient is positive, that means this value goes up. But the reason there is a peak down is, well, if you keep going up, you need to come down to match to the 0, because at this point should be 0. So it goes up to a peak and then goes down, so it can match to the 0. Then it goes down because it's on the right, negative. Goes down to a peak, but because it now needs to go back up to becomes matching 0, it basically goes up. Sorry, actually, not here doesn't match 0. It goes up to this point, then this matches to this modality, not the previous one. It switches the modality. It goes up for this modality and then goes down to match the 0. So that's how the gradient direction is working here. So right, let's see. This is just a summary of the equations. We have seen that. Now, there's a challenge here. So we talked about the score matching, and the idea of a score matching was that, well, you have these score fields that you compare them like you're using some Fisher divergence to see that how similar they are. One of the challenges that, well, if you have a lots of dimension, it could be optimizing this comparison, Fisher divergence, that divergence between vector fields and what we're predicting. So then the idea comes from a sliced score matching. So instead of trying to look across all dimensions at the same time for all the vector fields, maybe do 1 dimension at a time, like a slice it. So on what you will see here is that what we say, let's say we have this direction, this one on the left. We want to compare these two. So what we do, we bring a vector v, or some random vector, red one, project both of those onto that vector to a lower dimension. Okay, and then we compare them in that on that basically new projection line to make it cheaper, easier. So you have this vector field, the real vector field, and this is your score function, right? You want to compare these two. And what we are saying is that could we reduce the cost of this comparison, because in a higher dimension it's costly, this comparison. One idea is that yes, so instead of looking at this for comparison, let's do gradual comparison. So first thing we do is that I bring a random vector, same vector, and I project these arrows onto the vector. Okay? Then, instead of I compare the black arrows and the blue arrows in a higher dimension, I just compare them on 1 dimension that I projected them. Right? That becomes much cheaper. So that becomes the idea here, and we need to tweak the equation. So this was the original equation that you have without v. what we do, we need to project those on V. So in order to project this one on V, just multiplied by the V. And this one you also multiplied by the V. Projection of this on V, projection on this on V minus each other. Then you need to add another term, which is here, because V is also could be any vector. So you need to do expectation over points and point over these random vectors that you're projecting on. So it becomes additional basic expectation. Now, the idea will be that by doing so, hopefully we can find alignment and basically change the gradients across that projection, and maybe next time, next projection line and different V basically. And repeat this, that becomes computationally cheaper instead of we try to do it all together. So, question on that.
How do you come up with that random vector?
Well,
Like something like PCA?
think about the PCA, like for example, right? We do that, right? So you find which one can maximize the variance, right? Maybe you could focus on the original data, original random field, and fit the PC2, and then project the other one on that PC also. Now, if you want to look at it from the matrix multiplication, so you had this Jacobian, and it just multiplied by some random vectors, just ensure that it basically matches the dimensions or can calculate that value for you. So what we do, if we multiply it by 2 projections, okay, what you see in the forward pass after projection is kind of like becomes something like this. And if you again add another V, it kind of looks like this. Okay, we don't want to go in deep why this will look like that, but it will change your structured after projection to a different structure. Okay? So the idea, the steps that you want to remember is that so let me clarify in case you don't get the upper part. So I have a data, right? It's like during the training. Do a forward pass. What we say is that during the forward pass, I need to basically project my points on some vectors in order to do a comparison. So you project on a vector. Then you want to do a backward pass also, correct? You want to update, retrain. During the backward pass also, what we say is that, well, instead of trying to solve it all, project it again to another, maybe to the same dimension and compare it against that projection. So then you do doing backward, but you multiply it by another V, the same V technique. That becomes forward, backward. You do all of that on projections. The idea becomes like this. Sample bunch of data points, sample bunch of random projection vectors. That becomes your loss function. Just add this V here, and then add this V here, and that comes to the power of 2. And that just makes it a bit cheaper in case of if you have a higher dimension and you don't want to do all this Fisher divergence across all dimensions, you do one at a time, that becomes cheaper in some sense. So now all of this, okay, let's just connect this to the data generation. On the left, what you see is the original data modes that you have. There's some mode here, and there's like a higher density mode here. When you do a score matching, this is what we are going to learn. Okay, this is the score field. If you learn that the score field, you can learn this score function. The score function will be an approximation of that. It's not exactly, it's an approximation, but we want it to be as close as possible. After we have that, we use Langevin dynamics to generate image. The Langevin dynamic is in a reverse version. So during training, you add noise. During testing, generation, you remove noise, basically. Okay, so it's kind of like a reverse process. Now, the Langevin dynamic, it basically has the following thing that the point at a given time becomes the previous point times some epsilon, the gradient of this vector field plus this 2EZ. Okay, and Z is some random number. That's the idea of Langevin dynamic, or MCMC basically, was adding a random noise, or here removing a noise if you're generating. The idea here is that as K increases, the number of iteration, and the epsilon goes towards 0, this is guaranteed that basically will map to P of X. It's like it will converge.
We go to previous slide. So epsilon times the output of our model, right?
Okay. So think of epsilon like a learning rate.
Yeah.
Okay. What is this term? Gradient.
Yeah, but this is our model.
Log P, gradient of log P data. What does it? We estimate it, right?
Yeah.
What does it tell us? Vector field.
Yeah.
Which direction to go?
Yes.
You're denoising.
But what about the last time?
That's just account for that the noise that you have added previously. So you can look at it two ways. If you add noise, if you denoise, okay, you can use the Langevin in forward process to add noise to the data, or you can use it in a backward process to remove noise from the data. If you're using for the removing noise, then you use that gradient knowledge to tell you which direction to go because you wanted to make it more likely. Use it for adding noise, then you have, remember we had that acceptance criteria if the noise is good or bad. But normally this comes in during the generation. I'm going to see why. So now look at this example here. So the data, the blue, but you will see is going to be the noisy data, and we want to denoise it. This is technically using Langevin dynamic. This is what slowly will happen. So from a really noisy sample, slides remove the noise until it gets to the region with the high density, right? Because it's you gradually based on the arrows, which tells you that the gradient vector field, which direction to change the data. You remove noise from the data until you get to the value that's more has a higher density. Then we can look at this in two ways. On the left is the original score, like the score function. The one on the center is if you follow this score, and you just try to generate basic data, what will happen here is that this data becomes really dense. If you do it with noisy version of it, this becomes what you're learning. So, can anyone tell us why this might be better than this one?
Like 0, 1, like there's no.
This is going to be really sharp probability density. This is like a more basically wide. You have a more chance for learning or generating probability. Here, even if the point is likely, like close to this, you might get a really low probability score for it because it's kind of like a really sharp value. Now, the problem with this is that this is most of the time what you're going to learn. These models, they are not learning really good, being able to generate good data. And there are some reasons for that. We need to talk about that, try to fix that. And it's like stuck in some sort of like a local minimum in not being able to denoise. The main problem is like this manifold hypothesis. Remember in CNN, we talked about data, we went over this tangent manifold space. We did in CNN class. The idea was that if you think about an image in reality, it's like when you look at your image, you have a really high dimension in thousands, millions, and stuff like that, depending on the size of the image, right? But if you think about an image, in reality, image has actually much lower, real dimension, like intrinsic dimension. the image itself has a high dimension, but reality has a really low dimension. And you can think of any images. Again, if I have my photo hand like this, and I keep taking photos like this, and I just repeat this. And if you look at this image, this just has a really high dimension, but the actual image is that my hand is rotating on one axis, right? So the intrinsic dimensionality is low, but the image is on a high dimension when you have it. So that's the idea here, that the high dimensional data technically exists on a lower dimensional manifold. Okay, so high dimensional data exists in a lower dimensional manifold. Now, the problem that this concept has is when we sample point, lots of time the points get a low probability value. When you sample and you pass that sample to probability data, lots of time you get probability of 0, or close to 0, not 0, really close to 0. So this raises an issue for us, and that's why this score function, by default, this version will stuck in local minima, because there are two main problems. One is that, so on the left, this ring is an indication of the probability density. The arrow is pointing toward the center of the rings. That means where the density is higher. So if you're here, it tells you go this direction. If you're to go to that direction, as the basically we train and we learn better and better, what happens to probability density? Or then it becomes thinner and thinner, right? Because why? Because we are learning better about that distribution. So as these rings become thinner, what happens to the gradient? It becomes larger, because you are really far from those regions. The problem that arises here is that now, if there is a point that is not part of the real data, is not sitting on the ring, the gradient becomes really large. It throws off the model in the learning, because you are so far from this center. So when you have a new sample, like a noise, and let's say it lives here, it has such a high gradient, it will throw off the model in the learning. Even if the points are sitting on the ring, like on the edges of the ring, it is still going to have issues with gradient explosion. So these types of models, they're like, because of this concept, you either get a really high gradient for points that are off the ring, but for points that are on the ring and are more on the edges, you're also going to end up with some sort of like a gradient explosion. And it's also still possible for some points you even get a like a probability of 0, because it's just the model is not likely to have this. So as an example, so this idea of like this manifold space. So if you think about PCA, you can go from 784 to 597 without losing anything. From 3000 to 2000 without losing anything. That tells you that this data, they actually don't exist in this dimension. They exist in the lower intrinsic dimensions, right? Now, if you pass the same data, not after PCA, just the original data, to a score function, we don't have the image. The image is in the other slides. You will see that the noise is pretty high. It doesn't learn. It was like when you look at the learning, it just jumps so up and so much up and down with a really high gap, because the gradient becomes really off explosion, or becomes like almost 0. Right? So it doesn't technically learn. The solution to this problem is, actually we have this one, sorry. So the problem, the main problem, the pitfall here is that these types of model are really good, accurate for these regions where the density is high. They are really bad for this region where the density is low. So they are doing a really bad estimation of the region with the low density, good estimation of the region with high density, right? So what we want to do is that we want to see that, oh, well, how could we fix this to also have a good estimation on the center regions? So now there are some ideas. So one idea here is that let's add noise to the manifold. Okay, so let's basically keep adding noise. Ashkan is like,
You lost me.
with adding noise.
No, I'm shutting it down. I already learned.
So we know data exists in this manifold. Let's add some noise along this manifold to the data. Some of the point will even fall out of the manifold, technically. But the benefit of that is when you add noise, you always need to think about it. The reason we add noise is without noise, the distribution is really compact. When you add noise, you make it kind of like a wider and smoother. Just by simply adding noise to the manifold, you can get an accurate estimation on the center regions. Because you don't get all of a sudden really sharp gradients or really gradients like the p-values that almost are zero. Because you smooth out this distribution. Now, there is a caveat. How much noise could we add? So what you will see here is that on the left, this is the density function. Here it is the data as we perturb it, it's like a score field, and this is the estimation. As we add noise in the center, the red means that we added more noise. We do much better estimation for a score function, but the image quality is going to be so bad. So we are able to accurately find the score function, really good estimate, because we added more noise. The problem we have is that the images, like when you generate samples, they don't have that good quality. If you don't add enough noise, your image quality is, it's kind of like okay, but it only is okay if it's from a region that with a dense value. For lower density regions, it's like doing a bad job. So you need to do them in between, something in between, like what if we have a medium noise? The challenge is that, well, we don't know what's a medium noise, what's a high noise, like where to draw that line. So instead, the idea will be that could we add noise gradually, like I was just just on sequences. Now, sorry, this is just a slide for talking about the sample quality. So this is what we wanted to get. This is what we get. Right. So the model learned a really good, maybe a score function, but when it generates samples, it's not a good quality, not a good resolution. Now, so this the idea here is that for the noise conditional score based. Noise conditional score based is that during training, you want to add noise sequentially. And as you add noise, you need to increase the noise level. So you start with a small noise, you go to a large noise during training. It's in this direction. So first noise is always smaller than the last noise. Then you can also introduce some relationship between noise. It's possible, or it's common that when we want to add noise, we do something like this. Noise 1 with respect to noise 2 should be equal noise 2 with noise 3 and so on. So you enforce that the gap between noises are not like a random, to have the same like a relationship. So what will happen here is that we try to find this term. This is the same Q. Here instead it's written P. The Q, the noisy one. And you add noise as you go. So on the left, you have one noise. On the right, you have different noise level during the training. So you start here, then you add different noise levels. The goal during the training is that to be able to go from different noise levels, the color lines, back to the black curve, which is the original data. When you do that, during the training, during the generation, you can sample from noise. Doesn't matter what's the noise level. Go back to the original data. Okay, that's the idea, like a gradually adding noise. Now, and this again comes back to the same equation that we saw. So we have this actual score function, and then we have this noise conditional model with like a score. Sorry, the actual score gradient field, and then this is the score function that we're learning for. Now, what you see here is that there is a small changes to the formula. There is this lambda I. And this lambda I is just I stands for the noise level. You have L noise levels, gradually you're adding. For every noise level, you also have this mixing coefficient, okay, like some value. Here, for simplicity, let's just assume this lambda equal this sigma 2. So we just replace it with sigma 2. Now, as you go through noise level, this is what happens. So here you have a high density. When you add noise, it spreads out the data. So the density of the distribution becomes smoother rather than to be like more compact. And the vector field becomes like a more like a easier to learn technique. You know, it's like it doesn't have sharp changes. Because in the first one on the left, the gradient vectors are really sharp. Either so sharp or it's going to be really like you have a gradient explosion. On the last one, because now the data is more widely distributed, the gradients are smaller, like smoother. Now, this is now the reverse of that process during the generation. So during the generation, you want to reduce noise technically. So you start with a large noise, reduce noise to get to a small noise. Like we basically gradually reduce noise. And this is how we do that. Langevin anneal sampling, data will be accepted. Basically, data becomes the previous data plus a learning rate times the score. A score is the arrow tells you which direction to go. That helps you with the denoising process. Tells you that if you go to this direction, it has a more compact distribution. So that becomes the denoising process. As you gradually release remove the noise, now this is what you will see. So those are pure noise, okay? The model will be able to just pick full noise and just generate an image from, or happy, Ashkan? So now, let's recap on the noise conditional score model. We saw there are two score functions that we could use. One of them was a sliced score function. The other one was denoising score matching. And the question is that which one to use in practice. Denoising one, it works better, okay, than the sliced one. Okay, so it's kind of like tends to converge better. Now, so what we see here, this is the same thing that you saw in the previous slide. You can basically, I don't think we will, you have it in your PDF, but you can basically expand this, take it to the power of to do integration by part, and then you end up with this this equation again. Okay, so your loss function becomes average across different noise levels. So the last term that we see, 1 over L, L is the noise level, the number of noise that you apply. If you apply 10 noise levels, so this becomes 1 over 10. Average across noise levels, the difference between noisy model and this term. And this term again, I leave it to yourself to just maybe try. That's after you expand the term above and do integration by part, you should get to the term below. So now talking about the noise concept, and there's noise scale, like how much we add noise, like, and what does it exactly do? So if you think about it, I have 2 data points. The red is one data point, the green is a different data. When you increase noise, points will overlap on top of each other, because this becomes like a larger region for this noise versus, and also the neighboring noise, the neighboring node or point. So when you reduce the noise, they become distinct from each other. So that's the idea here, is that you basically, you want this noise to be enough that you have overlapping among these points. Okay, so that's how we can smooth out the distribution. But also you want to, again, be sure that this noising has a relationship, that the noise over the next noise is always constant across all the noise level that you're adding. So you're just not randomly changing noise. So, so that summarizes to weighted denoising score matching, which again is just the previous slide. We're just expanding it on it, and we remove this sigma 2, and we basically get to this term. So this one plus this one. Just leave that for yourself to expand on it yourself. So that becomes denoising score matching. And this becomes the final slide, like how we make this process overall work. Sample some data for your model training. Samples, like decide a number of noise level that you want to add. So you sample noise, basically, for those levels. Then create this like a Gaussian. Remember, in order to create a noisy version, you need some Z to basically generate those Zs. Perturb the data with the noise and the Z that you got. Calculate this value on average. This becomes your error. You want to update theta. So if you do backpropagation, you want to do update with respect to theta. And that's it. So this becomes gradual update. If you do that, and if you're actually able to implement it, it will get to the point that, if your model converges also, that you will be able to bring the real data during the training, add noise to it, denoise it. When you are done, you need to use the Langevin dynamic. Langevin dynamic basically tells you that in order to generate image, generate a canvas, like an image canvas of pure noise, okay? Pass that pure noise to your Langevin dynamic formula. And basically tells you that if I pass the image, the pure noise, to my S theta that I have learned in the previous step, S theta tell me that how likely is that? Basically tell me which direction to go, update this image in order to make it more likely. So you use that knowledge, update your image. Then you pass the image back again to the model, sequential. You do this series of times and you get to the point that you denoise, you have a denoise version of the image, and that depends on how good your model is overall. Okay. So the that's the overall idea. Second.